All right, welcome everybody. I guess we'll wait a few more seconds here. I know probably a lot of you were at my first presentation, but for those of you that weren't, my name is Szymanowski. This is Advanced Parametric CAD Modeling, and I'm gonna be using Onshape here. I actually opened SolidWorks in case anybody wants me to use SolidWorks. I use SolidWorks to work all the time anyway. Yeah.
I love SolidWorks.
You guys love SolidWorks? You probably
my team does it. I love it.
Okay, you'd probably like
We used to love
Onshape.
SolidWorks. I'm the only one who uses it.
You'd probably like Onshape too. You probably
We
would.
have it, and I do not like Onshape at all.
All right.
To
To each their own. I'm an alumni and mentor of 103. I've been involved in FRC now for going on 12 years. I'm also a relatively recent mentor of 272. And currently neck deep in build season for their FTC team right now as well. I'm a mechanical design engineer. I graduated from Penn State. I design industrial automation equipment every day at work in SolidWorks. So that's why I know SolidWorks. I use Onshape all the time. So yeah, that's me. I'm going to get right into it here. I'm not going to go over really the really basic stuff with CAD. I'm assuming that there's some kind of proficiency basically in this presentation. So I'm going to describe what parametric is an option. You do direct editing kind of on top. You just keep building on top of things and you can't go back to where you started. And other simpler 3D modeling programs as well. The other important thing with parametric modeling is that the order of operations, the order in which you model things and sketch things is very, very important. And that knowledge and background comes with time and with sketching. You're not going to get better at CAD without CAD. And I mean, that can be anything too. I used to CAD stuff that was sitting on my desk all the time just to get better at CAD oftentimes. Nothing specific, just to get familiar with how to sketch things and what's the best, most efficient way. But the order matters, and I'm going to go through some of the tricks and tips that I use for how to choose in what order I sketch things, and specifically related to FRC as well. Yeah, and then the cool thing is that parameters in sketches and features can reference other parameters and variables later in the model as well. So you basically, you can set something up once, and then use that throughout your model, and then if you change that one value, it will change wherever else that value is used throughout the model as well. And that doesn't have to just be a number too, it could be a pattern, it could be a shape, it could be a line, it could be all kinds of different things. It's really pretty powerful software. So I'm gonna go over the feature tree real quick. Some people, when they jump into CAD, they don't really take the time to understand what's really going on in the feature tree, so I have a quick slide on that. And this is the area where order is really important in the feature tree. So I have both, this over here is SolidWorks, and this is Onshape. You'll notice they're pretty much identical. SolidWorks has a few extra things at the top, but they start out the origin and the planes, and then they have sketches and then features as you go down. And each of one of those are in order. So for example, this 3D sketch was pretty much the first thing that was done in this part in SolidWorks. And that x-axis sketch was the first thing that was done in the Onshape parameter, and then the first revolve happened after that. So the order matters. Now the cool thing about this feature tree too is these things can be reordered. So let's say if I have a fillet or a chamfer down here, maybe I wanted to, or maybe I have a fillet or chamfer up here, but maybe I added more parts further down the list here, but I wanted to fillet or chamfer them too. I can click and drag that down to after I made those features. Literally just click and drag it and pull it down and add those fillets and chamfers to those parts that were made after the fact. And that's a way to keep the number of features in your feature tree low, which should be a goal as you're modeling. And so you have one feature that's defining multiple things, one feature that's defining as many things as possible. Features can always be modified later. That's the whole deck of cards description. And as I mentioned, multiple features can reference a single sketch or plane or value or all kinds of different things. And the cool thing, what I really like about Onshape, the specific reason that I like Onshape, is that you can create multiple parts with one sketch and one feature in Onshape, which is something that is unique to Onshape so far. SolidWorks doesn't have this capability, and no other mainstream CAD program has that capability right now. So that means you have, in Onshape, you have what's called Part Studio, which is a little bit different. You don't make individual parts. You make all the parts in one place and then import them into an assembly afterwards. And I like to call the feature manager tree the parameter navigator. I think that's a better name for it because it just allows you to work around your parameters and see where they are in the grand scheme of things. I'm going to get into sketches because sketches are sort of the backbone of good 3D parametric modeling. Up here I just have two quick examples. The one on the right is just the standard, when you do the tutorials on Onshape, that's one of the first ones that comes up. It's just a type of clamp. And then this is a kind of weird swerve design that I was working on. And maybe I'll open it up, we'll see. I'm going to go into best sketch practices. The most important thing is, again, where you're starting. You want to have intent when you're designing in CAD. You want to think about how these things are going to work out as you're drawing them. So you also want to think about where you start these sketches. I usually say that my top plane is basically the floor when I'm drawing something in CAD. So when I draw a robot, I won't start a sketch necessarily on the top plane. I'll usually start it on the right plane, looking at the side of the robot, so I can draw the wheels and draw them tangent to the floor, so that the robot's resting on the floor. And that way your zero plane is actually zero, and then when you do center of gravity calculations, they're from that zero plane. So you can know exactly where your center of gravity is relative to zero. Generally, you want to try to minimize features in the tree, as I mentioned before. So you want to try to do as many things with as little features. There's some exceptions to that, but that's the general trend. And you also want to center the part on the origin for the most part. So like your robot, you want your robot, the dead center of your robot usually to be the origin. The point at which you would rotate a valve with a tank drive usually should be the center. You can do it differently, but then you have to consider your center of gravity calculations for that as well. Construction geometry. A lot of people don't use construction geometry. I use construction geometry all the time, and for those of you that don't know what it is, it's lines in sketches that don't do anything to define the actual bounding box of the feature or the shape, but they just help you align things or set a dimension or give you a layout position or an alignment for something. That stuff is so important to use, and you can use it very easily and switch between construction geometry and regular geometry. You should really, when you're sketching, only use dimensions as a very, very last resort. You should be driving almost everything in your models with constraints. And a lot of times when you're sketching, like when you make a line, it will automatically generate constraints. And that still counts. But you should really only be dimensioning as a last resort. Dimensions are necessary. You're going to need dimensions at some point. But try to avoid them as much as possible. So for example, in this sketch, I only dimensioned one of these diameters here. This is a bearing bore. That's an inch and bearing bore. So I know that all my other bearings are going to be inch and an eighth. So there's no reason for me to dimension each and every individual one of them. And the same thing for these radiuses. I only define the radius there one time, and then I set it equal for the rest of them. So keep as minimal dimensions in your sketches as possible. And also avoid in context. This is more a thing with SolidWorks. This kind of doesn't exist too much in Onshape because of the way that part studios work. But in Onshape, you can do features within an assembly. And sometimes that breaks things. And it also makes the model run a lot slower. All right, moving on. Layout sketches. This was kind of the main thing that I went over in my first presentation this morning. This is where you can get a really, really good idea, most in 2 dimensions, of how things might work for layout. And how I lay out all my things is I think about what my end goal is, and then work backwards. I don't really care what my mechanism looks like. I just care how well it works. That's it, right? And you guys should think about that too. Maybe you have some aesthetic goals as well. I'm a very function over form kind of person. But I always, for example, I draw the game piece first. And I consider how the game piece is going to interact with my intake rollers, if I'm doing intake rollers or if I'm doing a grabber. The first thing that I draw is the rollers. I don't care how the rollers are going to end up in that space, I just care where in space they are. And that's the first thing that I'm drawing. The first thing that's interacting with the game piece. And then from there I go and furthering down the line, you then model the features that drive the mechanisms, so the chains, the gears, the pulleys, whatever it is. And then you model the features that mount the mechanisms, that hold all that stuff in place, so the plates, the pivots and the bolts and that kind of stuff. So you basically work almost completely backwards from what it seems like it would be. You start at your end goal, you work on where the end effectors physically need to be, sans all the other hardware and driving components. Then you figure out how they're going to be driven. Then you figure out how all that stuff is going to be held in place physically. And then you figure out how it's going to be mounted to the robot in that order, in that very specific order. You can, in these layout sketches too, you can simulate motion. In this sketch, I forget where I had it driven. But I had a dimension that it could convert from a driven dimension to a non-driven dimension. And you can actually open these and see how they pivot about this point right here. So that I can see how it would actually grab onto the cubes. All right, constraining in 2D sketches. Generally speaking, when you're modeling, you want sketches fully constrained. There are some exceptions to that, but very few exceptions to that. And constraining is, in 2 degrees of freedom, you have X, Y movement, but also rotate. So that's like on a plane, a piece of paper on a table can only move in the X direction, the Y direction, rotate. That can describe any motion of that piece of paper on the table. 3 degrees of freedom, or sorry, 3 dimensions are 6 degrees of freedom. You add in the Y, and then you also add in the B axis and the C axis, respectively. So it gets exponentially more complicated with adding another dimension in that. And the goal when you're constraining things is to eliminate all those degrees of freedom. And both SolidWorks and Onshape and all other CAD programs have visual ways of representing fully constraining things. In Onshape, sketches that are unconstrained or under-constrained are blue. Lines become blue or points become blue. And in SolidWorks, and they become black. And then in SolidWorks, I think it's the same thing or something similar. You can change it in SolidWorks, I think, so you can change whatever colors you want to be. I think stock gets blue and black as well. These are some quick 2D constraint examples just for people that aren't familiar with fully constrained systems to try to picture in real life how this would be constrained. Sure.
How is number one under constraint?
That's a great question. So number one, if you had this triangle on a piece of tape, on a table or whatever, and you had these 2 pins in place, do you agree that this triangle could be rotated in that position? That is one of the degrees of freedom. It's not fully constrained because it can rotate. It's not fully constrained. All right. So generally for anything you need 3 points of contact. This is over constrained by definition because if you had this situation, you could have a situation where it could be an interference with that. You have 2 things that you're telling the computer to do or the system to do, and it can only accomplish one of them logically at any given time. You have conflicting constraints, so to speak. So you're looking for exact constraints. You don't want over constraints. Generally, you definitely never want over constraints, and generally you don't want under constraints, but there are some exceptions. All right, does anybody have any more questions about that kind of stuff? Cool. These are the constraints in Onshape. For the most part, they're self-explanatory. I'm not going to go through each one of them. Coincident is just point on a line or point on a point. Coincident in Onshape is actually two collinear lines as well. SolidWorks has a completely different constraint for that, which I find aggravating. But the two important ones that I want to point out that I use all the time that I don't see people using often are equal and midpoint. Equal is fantastically useful because you set one thing in one location with one dimension and you can set it equal to each other. Equal is a good way to set a bolt pattern as well. You draw a bunch of dots, you put lines between them, and you set all the lines between them equal. And then you know that that's a bolt pattern no matter what. You maybe just dimension one of the spacings and then they're all equal. And they can be automatically centered that way as well. Go ahead.
What exactly is the normal to and pierce?
So normal to, this drawing shows it well. If you have a curve, any kind of curve, and you draw a line into it, normal means perpendicular to a surface, kind of, because it's not necessarily perpendicular. It's the angle between here and here is the same.
Okay.
Does that make sense? That's
Yeah.
normal to. So this line is normal to this curve. And pierce has to do with sketches in different planes. So for example, if I have a sketch on this plane, right, that has a line that's coming out this way, maybe there's a possibility that I would want to put a point on a sketch in this plane piercing through that line. Does that make sense? And that's a possibility in those CAD programs. So you can use one sketch's one dimension to constrain something in that same dimension over on another sketch that's in a different plane. So instead of redimensioning it, you can have them reference the same thing, which is super, super useful. I never, ever used fix, and I don't suggest anybody uses fix to constrain sketches. You should always constrain things from either the origin or existing geometry of your part. And you should always reference it from the origin as well. Cool, that's constraints. We're gonna go into parts. So let's talk about features for a minute. Most features start with sketches. Almost all features start with sketches. Some require closed sketches, so an enclosed 2D sketch. And some directly edit the model, such as radius, chamfer, draft, and thicken. The primary ones that are used though are these guys here. Extrude and revolve are probably number 1 and number 2, especially in FRC. There are some sweep and loft applications, but mostly extrude and revolve. And each of these features contains editable parameters, so values that you can change or settings that you can change about how that feature produces the physical, the 3D model. Let's see. So I want to talk about the Onshape studio modeling too. It's cool because everything is already in context purposely. You can make multiple parts in one studio, in one location, which is super, super helpful. Instead of having, so in SolidWorks to accomplish the same thing, you have to make a dummy part that has a sketch in it and insert that sketch into every single part, which is a pain. It's a total pain. This does that. This is sort of built into that for you. I'm actually doing that at work for a system right now. It's, I wish I was using Onshape for that application because it's so much better. I'm not going to go into that. Maybe we'll see it in some of the models that I pull up. A few best modeling practices. Center the part of the origin. Model only one instance of any part. So like if you have a mirrored part, or if you have a part in multiple different places, don't make it twice in the model. Just copy it or do something else that you only have one instance of it. And then also minimize the feature tree. You want as little features as possible, which just makes the model lighter weight and easier to manipulate and calculate. I wanted to do a little quick exercise with everybody here. So I have a few different fun things here. So these V blocks, these are commonly used to manufacture like round things or things that might not sit in the vise extremely well. So what do you think would be the best place to start a sketch for the V block? What's the first place you'd start it?
Probably on the front or right plane.
Good. And what kind of extrusion would you do?
Just a standard extrusion.
A blind?
Yeah, measured.
Measured blind. Would you do a mid-plane extrusion? These are the kind of things you have to think about. So
It depends on what's in the center. Depending on something in the center, I can't see like the entire geometry of the thing.
no, so certainly. But generally, you want to have your part centered on the origin, right? So you would want to do a mid-plane. Mid-plane just means it extrudes the same amount one direction as it does the other direction. And the total width of the part is that kind of extrusion. So for that, I would definitely do a mid-plane extrusion on the front plane, as you said. Perfect. How about this hammer? This is just a custom-made hammer that somebody made. Go ahead.
I might start off with the shaft of the hammer and use a revolve extrude for that, and then on the top of there is where I would probably use some lofts to finish off the hammer if need be.
Okay, that's interesting. I didn't even think to do lofts on that. But that's an interesting way to do it. Cool. I think that'd be fun. So you're saying you'd revolve this and then do like maybe a sketch here, sketch here, sketch here, sketch here to do the lofts.
Yeah.
Cool. Interesting. I like it. I would probably do a revolve for this and then cut away the flats. That's the only difference that I would do, but I'd do otherwise exactly the same. And how about the table? The table's actually, I'm going to show you guys a cool feature in Onshape and in SolidWorks to make this table in like 2 seconds. Any idea where you'd start that drawing? Sure.
I'm thinking maybe from the top.
Okay. Okay. Why from the, and what would you sketch on the top?
Maybe the top of the page.
So where would your top plane be? Would your top plane be here?
Yeah.
Okay. I would suggest that you make your top plane the bottom of the table, actually. And it's kind of counterintuitive, but the floor, like I said, for almost everything that I model, including at work, the floor is the top plane. Which, again, a little bit counterintuitive in terms of the naming, but so I would do that. But I wouldn't necessarily even start my sketch from there. I would start my sketch from somewhere else.
I'll sketch one of the side and then extrude out and then just cut the access.
That's an option too. Do you guys know about beam tools? Oh, we're gonna have some fun today. I think you guys are gonna love this kind of stuff. All right, I'm gonna get into CAD. I'm gonna show you, I'll show you how you can model this, but I'm gonna do it in terms of FRC. FRC robot. So there's a tool called a beam tool where you can draw a shape, like a profile of a shape, like a cross section, right? And put it in another part, save it out as kind of like a standard. So like 2 by 1 or 1 by 1, 2, right? Those are pretty common stock that people use. Or let's say 80-20, 80-20, like a common extrusion shape, right? You can then make a really simple 2D sketch that defines where the main members are, and then use a beam tool that will do all your coping and everything for you automatically. So I'll go through that. So let me just refresh and relog into Onshape here. Look here. I have all kinds of fun stuff going on. So the other thing that I really didn't talk about a whole lot is variables. I use variables a lot in CAD, especially like during the early part of the season when you don't know exactly what size your robot might be when you're still making decisions on that. So here you'll see I have a variable for wheel diameter. I have the base length, the base width. I have the center drop defined in here. So this is like a standard West Coast drive, which is ironic because 103 hasn't made a West Coast drive in like 3 years now. So, but it's fun to model. I have this wheel spacing, which this calculation is done using a chain center-to-center calculator. If you guys don't know, chain, depending on how many links you have in the chain, has very specific dimensions on center that you should use to calculate and define how your robot is designed. And then I have wheels per side. I'm not using this right now, but I was trying to set this up to be configurable where you could type in 4 wheels per side, if you really wanted to 2 wheels per side. Still working on that right now, but I'll go through how I would model this, how I'd model this. So I always start out with a side layout because that's how you can define how your robot is directly on the floor. Whoa, that was a little far. So the way I define a center drop is this line here is on the center of the main drive rail. So this is obviously a piece of 2x1 drive rail. There's the 1 inch. There's the 2 inch. So I have the wheel defined by that wheel diameter, so that's a variable. So if I went and changed if I went in here and changed that variable, it would automatically change the wheel diameter. And then my center drop, it's a little bit tricky to understand, but this is the center point of this line here. And I have the wheel dropped 1/16 of an inch, which is half. It's my center drop divided by 2. So that's actually an equation. So if I wanted to increase my center drop, all I need to do is change this variable up here, and it would automatically redo that calculation for me to set the center drop. And then I have on the flip side of this, this shouldn't be, oh yeah, this is the between the two. So this is how high the other wheels on the ends should be to make up for the rest of the center drop. So this is all done by those equations. So this is a really simple, easy layout, and then I just have, the tricky thing here though is to make sure that this isn't a vertical dimension. This is a dimension that's actually parallel to this line here. It's very important because if it's not parallel to this line, if it's not a slightly projected angle, you're going to have the incorrect center to center spacing on that chain setup. So again, this was really quick. Notice the 34 is the base length, same thing. So I can now come into this model, and if I say, okay, maybe 34 is not quite long enough, maybe we want it to be 36. I can come into here and it automatically changes my length to 36. And it just sets up the model really easily. The next thing that I do is I put a plane on the bottom of the of where the drive rails end up. So where the 2x1 tubing starts. And the reason I did that is I want to make a sketch at that level to define where my tubing is. And so this frame layout sketch has that all ready for me right now. So I made this sketch, and this is on that new plane, which is defined by the base width. And this is just a number that I set for how far the rails are away from the outside of the robot, the full outside of the robot. And now I can use this sketch with something called the beam tool, which is over here in Onshape, and it's called structural elements in SolidWorks, I think. Let me pull SolidWorks up. Weldments, it's called weldments, that's what it is. Structural members, weldments, it's the same thing. So I'm going to do beam. I'm going to select a custom beam shape because it doesn't have the standard that I want, the 2x1 tubing. I'm going to select a custom one. I need to find it, which is in my Onshape, and I call it profiles. FRC extrusion profiles. So in here, I've just made a document that has a bunch of 2D sketches of different profiles. And I use this for all kinds of stuff. So I have regular hex, I have churro, I have L angle 1x1, I have thunder hex, I have, so this sketch is centered on the tubing, this sketch is on the corner of the tubing, and this sketch is on the mid base of the tubing, so I can do all kinds of different locations for where tubing is. So in this situation, I drew the complete outer perimeter of my robot, so I want to use the 2x1 100 corner tubing profile. So I'm going to use this guy, and I actually made those sketches. Oh, what the heck? All right, we'll try this again here. I have internet. It just timed out or something. So beam, custom, here, I could select the lines or arcs that I want my corners to be. So does everybody see what's happening there? So that's one, and if I click this one, it's not gonna put it in the right place. So you have to go by and do this a few times, one by one. So I can pay one. And then I'll do another one with the same profiles. And the line that I want for this one, I need to see that sketch again. Would be probably this guy here. And I want to trim based on this face here. So does everybody see I can do that? Actually, I think I could do this in the future. I think I could just select all these lines and choose where it's trimmed. Yeah, good. So we're gonna trim, or we're gonna miter. That's what we're gonna do. Vertices for part joints. You can choose where you want your joints to be. Alright, this isn't quite working as I intended it. But it's very, very easy to set frame designs for stuff like this. And in some cases, you might just want to make one side and then mirror it. But in other cases, you might want to do the whole thing at once. I'm going to try just doing one at a time this time. Apologies. Show sketch. I'm going to do this kind of thing. I'm going to trim it to this face. So see how it basically automatically shortened that for us. It didn't quite do that on this side. So maybe I should mirror it first. Okay, here's a good example of parametric modeling. I go basically back in history, and then I can do a mirror on the front plane. I want to mirror this guy on the front plane. And then I can go back to this beam, and I can also trim to here. It trims it between there. And then I can make my one drive rail. Now, technically, the other drive rail should be the exact mirror of the one. So I should wait until I'm done making this drive rail before I mirror it as well. That's another tip. You want to do your mirrors after you have all the features from the part that you just want to be in a single part. You don't want to mirror something and then add features to both parts. It just adds features in the tree. There's no reason to do that. So yeah, that's that. Then I can use this layout sketch. For example, I can make a new quick sketch here on this space and then reference. I'm just going to draw them up here. You'll get the idea. I'm going to select all these wheels, make them all equal to each other, and I'm going to make them equal to this wheel too because that's exactly the size that I want. Or no, I don't want to make it the same. These are my bearing holes. That's right. But if I just dimension one, the size of the bearing. Now they're all the same size. We make this one coincident with that one. This one coincident. Got to make sure you select the right one for stuff. And this guy here. And you can also mirror this left to right too. It's an option. Then you can just extrude, remove away where your bearings are. Just do extrude all. And there you've got exact locations of bearing holes for a standard West Coast drive with exact center to center spacing. So
If only it was easy to drill holes then.
sure.
If you were gonna do lightning on your side tubing, would
Sure.
you just do that on the same face that you were working on?
Yeah, pretty
You
much.
can offset and then make it in?
You can, sorry.
Like an offset of the bearings to make sure there's enough space to support
Yes,
them.
yeah, absolutely. In fact, Wow, Onshape has a fantastic, what's called a lightning tool. Maybe I'll show you how that works real quick. If you want, I can go on to other more.
She brought it up, I think we should see it.
How much time do we have? Because there's other.
You have 18 minutes.
I have 18 minutes. All right, I'll show you real quick what that's gonna look like.
She wants to see it. I can see it.
Lightning fast.
I'll click it as.
Zoom in.
I'm just gonna draw this, and hopefully this will be showing enough. It has a tool, it's called Lighten. You select the sketch regions that you want to lighten. So I drew 3 lines, right? I drew 3 lines, and you have the thickness of the webs that you want. That's what the thickness value is. You have the tool radius, so this is 0.2, but 0.2 isn't a normal size tool. Let's do like 3/16, which is an actual tool size you can buy. So it automatically makes these inside radiuses 3/16, and I did that with 3 lines, or 4 lines, in like 2 seconds. Normally in SolidWorks,
Yeah.
you'd have to basically draw out each one of these triangles, or maybe draw one pattern of them and pattern them throughout
Yeah,
the whole thing.
our team uses Fusion, and what you would do is just draw in the offsets for the bearings to give them support, and then
Yeah.
draw in your lightning and then fill in everything.
But that's a pain, and this
It's a
does it
pain.
automatically.
Yeah.
I did this in
Yeah.
10 seconds, and I could have gone more into detail, made them equal and pretty and
Yeah.
stuff, but.
What if you click like to the region where it interacts with?
Oh,
the
over
parent
here?
wall?
Okay, yeah, sure, I'll show you what
That's
it
what
does.
happens then.
A little sad that we're excited about
Nah,
that, but nonetheless, that's.
I'll do this one too. That's not reasonable. You'd want
Yeah.
more material in there, but
The lightest chassis ever. Has no metal in it.
but this makes making lightning patterns stupid simple and quick. Yeah,
Lightning makes
yeah.
it
So highly suggest using the lighten feature. So this is actually a feature that like somebody else made for Onshape. That's the cool thing about Onshape. There's like a code base that they release to the public, and you can make whatever kind of feature you want. There's companies that are making their own like database of programs that do exactly what they want to do within their company. But this one is one that a lot of different companies use to lighten their products, and we can utilize it in FRC to make awesome lightning patterns in seconds.
You can make a chassis in like 30 minutes.
Absolutely, I've designed chassis in just about that time. I have. It's extremely powerful. Yeah. So that's lighten. I'm glad you guys appreciate that, because when I found that, I was like, wow, that saves so much time. Yeah, so for those of you that don't know, you have to make basically each of these individual shapes on your own, like with individual sketches and cut it out, or just make triangles and then fill in every single one of those corners, which is also a pain.
That's what we have freshmen for.
Well, freshmen can use Onshape and do it in 2 seconds. All right. I wanted to talk about pneumatic cylinders and using pneumatic cylinders to actuate, let's say, an arm, because I think that's something that teams do all of the time, and it's something that teams aren't necessarily good at. But it's something that there's actually a design to. It's not something you just bolt an arm on somewhere, try it, see if it works, then move it and do something else. You can actually design 100% where your arm is going to stop when the arm is fully extended with the pneumatic cylinder, where it's going to end with the pneumatic cylinder. So I'm just going to draw it really simply in 2D. I'll just make a new bar studio here to do this. So pneumatic cylinders, the cool thing about pneumatic cylinders, they have 2 positions, right? Generally, I mean, you could buy a 3-position cylinder, but generally pneumatic cylinders have 2 positions. You have an extended position and you have a retracted position. So you can use those 2 positions to figure out exactly where an arm would be and where it would end. So I don't know exactly the lengths of pneumatic cylinders off the top of my head. You have to go to a site like Bimba, or go and grab a physical pneumatic cylinder that you have, measure its extended length and measure its retracted length. and then use that in your model. So you need some numbers before you dive into this, but I'll explain what's going on. So let's say I'll draw a really quick robot here. We're just going to draw one wheel in the center just so that we have something to define a height. Or we'll make that tangent to the top plane. And then this is going to be 3/6. Sure. I'm going to make this all construction geometry for now, so it doesn't bother us too much. So let's say you have a roller on an arm. I'm drawing these on an angle purposely because if I didn't do this, it would automatically give them vertical constraints and horizontal constraints. So even though I may want them to be vertical and horizontal at some point, I draw them on an angle so that it doesn't make the constraints automatically. But I do want them to be perpendicular to each other. And I do want this to be mounted somewhere off the frame. I don't know, maybe 2 inches off the frame. And maybe, you know what, I'll draw a game piece, which might be a ball. That is.
It's gonna be a ball this year?
Yeah, I figured it out. I don't know, what's a ball size we haven't seen recently?
1 inch.
Well, 1 inch ball. We're going a 1 inch ball.
Field
All right,
research
cool.
already.
That's fine. That's totally fine. The other thing that you want to consider when you're drawing this kind of stuff, always consider your bumpers. So many people forget about the bumpers. The bumpers are an important part of the robot. Bumpers, I don't know the exact dimensions. I usually just draw them something like this.
I think they're about 2.5 inches in diameter.
Well, the noodles are 2.5 inches, but there's 2 stacked high. So it's usually 5 inches or 5.5 inches high, and they have to be a certain amount off the ground. All right, where is this one? This one's blocked somewhere. I use keyboard shortcuts too. I suggest that when you're CADing, you CAD with 2 hands, not just CAD with 1 hand. So we have 2.5 plus 3/4 inch plywood. So we're at 3.25, right? That's right. So there's a basic bumper layout, and let's make sure it's above the ground, a certain amount. All right, there's your bumpers. Maybe we should make our arm higher, 4 inches, so we're above the bumpers. Cool. And we'll make it. We'll make it. That's a crease. This is vertical. Make it 3 inches from the edge of the robot, or maybe 2 inches, 4 inches. All right. We want now. So if we have a 1 inch ball.
On the ground.
So I'm gonna use a center point arc that's gonna rotate around my wheel, right? And the distance between here is gonna be 1 minus whatever the compression that I want between the wheel and the ball. So I'll do 0.01. And I'll do more. I'll do 3. And then I'll make the roller diameter 1.25 or something. I don't know. We'll make these. Make this and this go in here. And I'll make this and this perpendicular. You'll see what I'm doing in a second. So if you want to pick up 1 inch balls, maybe you can use something horizontal.
You just need a vacuum.
What's up, Q?
I said maybe just use a vacuum.
Pick up 1 inch balls if it's something bad idea. All right. Let's try this. 1 inch balls is probably not natural.
High waist.
So you agree that when this is on the ground, this will be able to pick up balls in some way, shape, or form, right? So I'm gonna set this to, I don't know, 12 inches. And I'll set this, for now, we'll set this horizontal with the ground. Temporarily, it won't be there forever. We're gonna set this to 4 inches. All right, cool, so we have, actually, let's do less than 12, we'll do 6. 6 is a bit low. 8. Cool, that works. So it's right up against the front of our bumpers, it picks the balls up, maybe this is like a conveyor system that picks it up against the bumpers, but who knows? But you get the idea that this is an arm that would fold back into the robot, right? And then come back out. So what you can do is set up a point maybe where you have a pneumatic cylinder. So let's say at the midpoint of this, and this is just for simplicity's sake that I'm having this in here. That's 1 inch long, and let's say the full extended length of our cylinder, which is going to be what the circle is that I'm drawing, and you'll understand this in a second, is, I don't know, 14 inches. I'm literally just throwing numbers out there. You would use an actual cylinder that you have, that you know the dimension. What's up?
You said 14 inches.
It's true, yes. So this is a radius because it's a diameter. So this is a 7-inch fully extended cylinder, right? And then you have, when you put your arm up, what we're going to do is we're going to select all the things that we want to rotate. It's going to be all this good stuff here. We're going to do a circular pattern, which in on-shape is a bit weird. You have to click and drag. Circular pattern here. And then I want to make it just 2 times. And I want to change the angle until it's just within, it just is within the robot. That's all I really care about. And we're going to do that. Oops. Sketch. So this is where we want our arm to end up, right? And this is probably going to need more actually. Let's probably get. And then let's say the retracted length of our cylinder is, I don't know, on a 7-inch stroke, a 7-inch full extend, what would be forward?
Oh, 7 full extend.
Yeah, 7 full extend would be retracted
So,
forward.
That's a 3-inch circle.
So 8 inches. So 8 inches. Okay. So so where these circles intersect is a really important point. And it's actually really cool. It kind of looks. It's a very messy sketch here. What you're looking at. But where these circles intersect. So at this point right here and at this point right here are where you would mount a cylinder so that when it extends, it puts the arm from this position to this position. Now, this one doesn't really make a lot of sense, right? If the cylinder's here, when it extends, it's not going to rotate the arm this way. So that one we can instantly rule out. But this one, if you have the cylinder here, right? When it's in this position and it's retracted extension, it's only here. And then when it extends, it ends up over there. It's a little bit confusing, this layout. But this is how you figure out where pneumatic cylinders would be mounted on a robot. And now you can come in here and let's put in a different cylinder. Now, like let's say instead of 7 inches, it's I don't know, it's a 10-inch extended cylinder. And I'm going to do 10 times 2 so that I can automatically. And what I would normally do is I would make a variable for this, and I would just automatically have it update. I would automatically have an equation in here that would multiply it by 2. So I could just update the value, the stroke of the cylinder. That would make it a lot easier. And then so if it's extended 10 inches, it would be retracted, I don't know, 5 inches maybe, 6?
7, yeah.
6 or 7, so this would be, we'll say 12. So now that cylinder would mount here at this point. Does that make sense? So now we can use that to make a bracket or something where the cylinder needs to be mounted. put a bearing on it too, or no, it's just a bolt hole. So this could be 0.25 inches. And this would be tangent. Does this make sense to everybody? It's a little bit confusing, but you can imagine that there would be a cylinder between here and here that is retracted, right? And then when it extends, it pushes the arm out and rotates over to here. And if you know the full extension of your cylinder and the full retraction of your cylinder, you can figure out exactly where it needs to mount in CAD before you even have to drill any holes, which is extremely, extremely useful. Trial and error can absolutely get you to this kind of same location, but trial and error also requires a lot of actual parts and tools and energy and usually money. Whereas CAD is it's a pretty quick and dirty way to accomplish the same thing where you can make a bracket automatically. Would anybody like to see me quick draw out any specific thing? Actually, I have a really cool thing that I made that I want to show you. I think next year's game is going to be a shooting game.
Me too.
Thank you.
No, game, this is gonna be a cylinder.
Water game.
So, for you guys that didn't see my presentation, guys, please, for you guys that didn't see my presentation this morning, I modeled this, which shows like a cascading elevator. This is super simple how I modeled it. I basically made this line and this line equal to each other. Sorry, this line and this line equal to each other. And you can accomplish a cascading effect in CAD, in 2D CAD, which is really powerful. You can see exactly how something would lift in that case. So this is obviously 2018 in a 254 style elevator. But I wanted to show you, I made a mock-up of a shooter where you can change the diameter of the ball. So I already have a basic design for a shooter that once we figure out the design of the ball for this year,
1 inch I was.
It's gonna be a cylinder. It's one.
What's the diameter gonna be?
So,
I don't know.
1 inch, we knew that.
so this looks pretty familiar, right? This looks pretty, we're all pretty, for those of us that have been involved in FRC for a little while, this is the boiler for the 2017 game, and this is modeled to the right height and everything. And this is just a parabola that I graphed to explain it. But what I have here is I have ball diameter. This is the, I forget what that is, base height, the robot width, robot length, max height of the robot. This is the ball compression. So I actually put a variable in here for the compression of the ball, which is a very, very important thing when you're trying to determine, when you're trying to shoot the ball, but also like intake as well. So I use this compression value and the ball diameter. I set up another variable called height. The height is equal to the ball diameter minus the compression. And then I use that height value wherever I'm trying to pick up the ball. Because you want a certain amount of compression between the ball and your intake or your shooter. So what's cool about this is you can prototype this system with a certain amount of compression. And then if you determine that that compression amount doesn't work, you can go into CAD, change one number, and it updates your entire model. Your entire model, which is incredible.
Does it reach out and re-drill the holes in the robot?
Well, you do this before you drill any holes. That's the trick. That's the trick. All right. So I want you to take just a quick look at this model and notice that this is a ball right here. So the ball. The idea is you pick up the ball somehow and go in some kind of hopper. It'd be lifted up this conveyor and then end up coming out of this shooter here. Right. That's the idea. I want you to watch what happens when I change this ball diameter. It would probably work with 1 inch. Let's try. It's gonna look weird. But so this whole sketch, this a relatively simple 2D sketch, now has the capability. It's a conveyor for a 1 inch ball, and maybe it's not a 2 inch roller anymore. Maybe it's that's what the RD is. That's roller diameter. Okay, that's good to know. So I could actually come into here, and this roller diameter I can make it 1 inch instead of 2 inches. And I would also change that conveyor. So now I can go in here and do a ball diameter 6 inches. I had 4 inches. Looks like that. And I could go in here and do a ball diameter 8 inches. That looks like that. So this is where parametric modeling can get really, really important. powerful and allow you to make very large sweeping design changes with just a few changes in numbers if you draw it right and use the correct constraints and use variables intelligently. So yeah, does anybody have any questions? Sure.
How did you draw the parabolas in that?
I think it's just a spline actually. I don't even know if it's a parabola. Oh no, I think there's equation-based. What's the shear layout? I think it's an equation-based line. I forget how I made it. Yeah. It's so this is a parabola and its rho is 0.5. Apparently you do that in on-chip. I forget when I drew this. It was a long time ago. But yeah.
All right, great, thank you, Phil. And thank you everyone for coming to this year's boot camp. I hope you got something out of it.